All right, good morning, everyone. How did your homework go? Okay, as usual, put your questions on chat so we can discuss them before we start the new material. Okay, can we do 19 and 30, of course? Any other problems? Okay, so problem page number 1. Number 19, so we will look at it, and 17. Okay, so I'll try to remember them. Number 19. The question is, find the points on the curve where the tension is horizontal or vertical. And if you have a graphing device, graph the curve to check your work. So this is a function which is given parametrically by x equal cosine theta and y equal the cosine of 3 theta. Okay, and the question is, where is the tangent line horizontal? So the tangent line is horizontal basically when this is piece we know very easily, when dy dx equal to 0. That's the derivative equal to 0. It means, since as we said yesterday, we don't have y as a function of x, so we express the derivative in terms of theta because they call theta the parameter instead of t. Means when this is equal to 0, it means that dy d theta equal to 0. Basically, it means when theta change, time change, y doesn't really change much. It means delta y over delta theta equal to 0. So now we just have to compute that. So it means, what's the derivative? So dy d theta, that's my y, and it's the derivative of cosine, it's minus the sine of 3 theta times the derivative of what's inside, times 3. If this is equal to 0, it means what? It means the sine 3 theta is equal to 0. Okay? Now, when is the sine equal to 0? For which value of theta? Let us remember the graph of sine. In general, that's the graph of sine. And the graph of sine is 0, at pi, 2 pi, 3 pi. Okay? So when is sine of 3 theta equal to 0? This is when 3 theta takes which value? Go ahead. So for which value this occurs? So let us here remember sine x equal to 0. When's the sine x equal to 0? When x is 0, right? Plus or minus pi, plus or minus 2 pi, and so on and so forth. So y pi, yeah, plus or minus pi. So in general, if you want to be, it means every time x has the value, a certain constant times pi, where k is an integer. So that's really in general. Every time k is an integer, that's when the sine is equal to 0. But that's the sine of x. In this particular problem, what plays the role of x is actually the 3 theta. It means when 3 theta takes the value 0, plus or minus pi, plus or minus 2 pi, and so on and so forth. It means when theta takes which value? 0, plus or minus pi over 3, so I divide by 3 across the board, plus or minus 2 pi over 3, and so on and so forth. So we can simplify this to write, it means when theta takes the value, a certain constant times pi over 3, where k is an integer. That could be positive or could be negative. Okay? please ask questions as I move on. So the idea is really boiled down to solve the sine of 3 theta equal to 0. So we move to the side that we said in general, when is the sine 0? The sine is 0 when the angle here is 0 plus or minus pi, etc. But what I have here is 3 theta. It means when 3 theta is 0 plus or minus 1 plus or minus 2 pi, it means I divide across by theta because I need a condition on theta. When theta is 0 plus or minus pi over 3 plus or minus 2 pi over 3 and so on. So this is when we expect a horizontal tangent. It means we accept the graph to look like this at those values, something like that. So we expect this, and this should happen at plus or minus pi over 3. We will try to sketch the curve later on, and then we see if we can make sense out of that. Okay, part 2 is when is the tangent line vertical? The tangent line is vertical, it means that's how the tangent line should be. And the tangent line is vertical when dx d theta equal to 0. It means as theta change, x really is not really changing much. And if we forget that, it's vertical when the slope goes to infinity. And the slope goes to infinity when dx d theta itself go to 0. So 2 ways of thinking about that. So tangent line is vertical when dx d theta is equal to 0. When does this occur? So what's dx d theta? X is the cosine. It means when the sine of theta equal to 0. Now, when is the sine of theta? There is no 3 theta involved anymore. It means theta is 0, plus or minus pi, plus or minus 2 pi, and so on and so forth. So we can rewrite this as when theta has the form a certain constant times pi, where k is an integer. Okay, so that's really how we do this problem. Now they ask us to graph it, of course, using a graphing device, and we'll try to do it with you. So I'm gonna see if I can share the screen and do it using a program called Desmos that I really encourage you to use because it's actually really nice. So I will share it and let's see if I can get it. Okay. And I want that. And I want the function. Okay, here I'm gonna try to input what they told me. So it's the cosine, and I think they want t, not theta here, so I will put cosine t and see if it works. Cosine 3t, that's that, and I want t, let's give a lot of values, see if it works. I want t to go from, let us say, from minus 6 pi, so I'm gonna put pi here, sorry. Let me see, I think it's going to take it pi and to 6 pi, just, sorry. And right here to 6 pi's and see if I get anything that makes sense. All right, so it gave me this graph. Okay, let me enlarge it a little bit. Let's make a larger range. So let me go from 20 pi all the way to 20 pi. And let's hope it gives me something that makes sense. All right, and it doesn't like what I'm giving it for some reason. Cosine t. I don't know why it's doing this. It should give us actually a very good graph. Let me check if it's in radian, everything. It should be in radian. Yeah, it is in radian. Okay. It's not giving me the correct graph. I will try the calculator and see if this one would work. So I will stop sharing screen. It just worked a minute ago. So I will try my calculator, because you should know that all this could be done using a calculator. So how can the calculator graph it? So if you guys have one, you can try it with me. You go to mode. So on a calculator, that's how it works. But I will use Desmos again for another problem. You go to mode, and when you go to mode, you go down to parametric, and you enter parametric, you enter it. So you have parametric, and now you go back to Y. Now when you go back to Y now, you're gonna have X1, Y1, which will give you both coordinates. So you can input the first one, which is the cosine of T. And then the Y is the cosine of 3T. So that's how you can use your calculator to be able to graph the parametric. And once we do that, we can go to the window, and the window gives us the values we want for the T values, the range of the T. So we can go from 6 pi to, let us say, 6 pi, and see if my range is good. And the T step means that you want the calculator basically to compute, because the calculator draw point, it computes value. So you want the T step, it means if you want to compute at 0, so then delta T at 0.2, for T equal 0.2, for T equal 0.4, that's really what's doing. Now X minimum and X maximum, of course, those are very large values, because my Y is a sine equal cosine, so they don't take such large value, and 2. And let's hope for the best now. I'm gonna graph it. Okay, it's giving me the exact same graph. I think what's really happening here, the graph is going around itself. The graph is going around itself. So those are where we have the horizontal tangent, and the vertical tangent are happening right here. That's what's happening in the picture. So the vertical are happening right here, and the horizontal are doing this. And you see this piece of the graph, because what's the graph doing is actually going around. So it's moving this way, then it's backtracking. Then it's moving this way, and it's backtracking. That's exactly what the graph is doing. That's why you have this very solid. I should have paid attention to that previously. That's why it's a very solid, because that's exactly what the graph is doing. Okay. So now we move on to problem number 30, and then we would move on to number 17, and then I will move to number 30. Okay. Number 17, we have X equal T to the power 3 minus 3T, and Y equal T squared minus 3. Okay, I will try to graph this sketch again using Desmos, because the first time I did not interpret it correctly, which was my mistake. So horizontal tangent. Horizontal tangent. That will occur when dy dt equal to 0. It means 2t equal to 0, t equal to 0. And the points on the curve, the points on the curve is, I should have found the points last time. The point on the curve will be, if t is 0, x is 0. If t is 0, it's minus 3. So at the point 0, minus 3, somewhere on the curve, at the point 0, minus 3, the graph is going to look like that. Okay? That's how the graph would look like. It's a horizontal tangent. Now the second part, which is vertical. The x dt equal to 0. It means 3t squared minus 3 equal to 0. It means 3 times t squared minus 1 is 0, which gives me t equal plus or minus 1. So we have vertical tangent for 2 values of t. Now let us find the point on the curve that correspond to each one of them. For t equal to 1, the point would be, my x is 1 minus 3. I plug in 1 for t, and my y will be 1 minus 3 minus 2. So on the graph, at the point minus 2, somewhere in here, the graph will look a little bit like that. That's really what I'm getting so far. Now, for t equal minus 1, what's the point? Okay, my x is t to the power 3 minus 3t. If I plug in minus 1 here, I will have minus 1 plus 3, which gives me a 2. And the y is t squared minus 3. It means at minus 1, I will have 1 minus 3 minus 2. So this tells me graphically that this is the point 2 minus 2. My graph will have to look like this at this point. Now let us go back, and I'm going to try again to share. I do not give up. To share screen with Desmos and see if we can have a graph which is okay. So I'm going to enter right here the function I have, t to the power 3 minus 3t. And I'm going to enter, of course, t squared minus 2. Okay, and that's the graph we actually have. Now, this is a very good graph. And let's see if it coincides with the values we have. Horizontal tangent is exactly right there. So that's where the horizontal tangent is. And why did we get 0 minus 3? The graph show it at, okay. I plugged in, we got 0 minus 3 because I did, this should be a 3. All right, now everything is correct. So that's the horizontal tangent, 0 minus 3. These are the points we got. And then the vertical tangent are right there and right there. They're exactly what we got. The horizontal tangent were at minus 2, that's the first one we got. And the second one we got was at 2 and minus 2. So those were the horizontal tangent. You can see that. Sorry, those are the vertical. We can see them. And this is the horizontal tangent we are seeing. So that's exactly how this graph would look like. Okay. Now we will look at the last problem that you guys asked, and then we proceed. Thank you very much, Ben. Okay, let's look at the last one. So it's number 30. And let's look at this one. Okay, and number 30. Find equation of the tangent line to the curve x equal. So we have the curve x equal 3t squared plus 1 and y equal 2t squared plus 1. And they want us to find equation of the tangent. And they put an S in here at the point 4, 3. Okay. Before we do this problem, let us a little bit, again, I will share the screen and let us a little bit sketch those curves. So we're not gonna sketch them, by plotting point. For now, we're just gonna do the same thing and see what point they are talking about, and then we do the problem. Okay, so again, I will share the screen with you. And I will enter the function, which is 3t squared plus 1. So it's a 3t squared plus 1. That's the first one. And the second one is 2t squared plus 1. So this tells me what I'm doing. So it's 2t squared plus 1. Okay. And okay, the graph is a little bit like this. We have to change the range a little bit. So let's take for range. Okay, let's take for the range of, I don't know, minus 20 and 20. Okay, and see what we got. Why is this not giving me what I want? Ah, sorry, y is 2 to the power 3. I was wondering what I did wrong. Okay, now it makes more sense. All right, that's the graph. Okay, and what do they want me to do? They want me to do, find the tangent at 4, 3. So 4, 3, right there, that's the point. And they want me to find the equation of the tangent. Okay, so how can I do that? So that's the graph, and so I know it looks like a positive number, whatever, because the slope here is actually, the line is rising here, and they want me to find the equation at this point. So who can tell me how to do that? Okay, who can tell me? Any ideas? So my graph seems to look something like that. That's my graph. My point 4, 3 is right here. And I need to find. So of course, Tim tells me you have to use, okay, the slope is equal dy dt over dx dt. Okay, I totally agree. So let us do that. And then you tell me what I need to find to be able to do it. What's dy dt? 3t squared. That's the derivative of y. The derivative of x is 60. So this will give me t, I guess. Very good. I need the slope, which is a number, a fixed number at the point 4, 3. So what do I need to find to be able to find the slope? The slope depends on t, but I want at this particular point. So what do you think I need to do to be able to figure out the slope?
Take the derivative.
I did. I got t, because the derivative depends on t. But I want the slope at a very specific point. Plug 4 in for x and solve for t. Okay, now it's making sense. What I have to do is, I would like to know for which value of t. So as I said in class, imagine you have an object moving, t is time, and an object is moving along this curve. And for every time t, that's its x and y component. So to be able to figure out the slope, I need to find for which value of t is my object at the point 4, 3. So I have to find when this will occur. So the question now, to be able to find the slope, we have to find the value of t such that the x is 4 and the y is 3. That's what I need to find. I'm asking myself, okay, when does the particle hit the point 4, 3? I need to find the time when this occurs. It means I need to find the t such that the x is 4 and the y is 3. So we need to solve for those. And let us solve for that. I want the x to be 4. This is equal to 4. And for which value of t does it occur? All right, this will give me 3t squared equal to 3. It means t squared equal to 1, means t equal plus or minus 1. So we have one value here and one value here. So the x coordinate is 4 for t equal 1 and minus 1. So that's the x coordinate. So it is 4 for two values. It's 4 for 1 and it's 4 for t equal minus 1. So now the question is, for which one of them is the y equal to 3. So I'm going to take each one of them and plug them in the value of y and ask myself which one will give me the y equal to 3, which is obvious in this case, and which one will not give me the y equal to 3. So if I take t equal to 1 and plug it back into the expression of y, I will get y is 2 to the power 3 plus 1. This is equal to 3. The t equal minus 1, for t equal minus 1, the x is 4, but the y is not a 3. So I need to set x equal to 4, solve for t, and then I have to figure out which one of them will give a y equal to 3. So this point occurred for t equal to 1. Now I know the t where the particle reached the point for 3. So now I know my t. So after I do that, I'm going to go back to the slope. Now I can compute my slope. So the slope now is equal to t. Now at t equal to 1, because that's the point I am interested in, the slope is equal to 1. Now I found my slope. I need the equation. What is the equation? The slope is 1. That's my slope of 1. The point is for 3. So the slope will be, the equation would be y minus 3, that's the y component, equal to the slope times x minus 4. And that will be an equation that you can rewrite it, of course, x minus 4 plus 3, x minus 1. Okay, so that's how you're going to find 6. So this problem is a little bit different. That's why I assigned it. So the idea is I need to find the slope very well, but I need to find, so the slope depends on t. The slope depends where I am. The slope is changing. So the question was, find the time when your particle is at the point for 3. And to do that, I plug in x equal 4. I solve for t. I found 2 values, which makes sense. X is 4 for 2 different values of t. Then I'll have to pick up the one that gives 3 for y. And t equal to 1 is the one that did. Okay? Any other questions beside that? So is there one more idea for parametric curve before we move on to the following section? And this is the idea of a length of a curve. So here is the problem, length of a curve. Okay. Now, we've seen the length of a curve when the curve is given by the graph of a function. So let me remind you what we saw so far. So suppose we have, that's something we've seen before. Suppose you have, this is f of x, so a function, and that's the point A, and that's the point B. And this is the curve that's given by the graph. So this is the graph of f of x. So that's the graph. It represents a curve. And what's the length of the curve? And I remember telling you in class, means if you take this curve and stretch it and measure it, what length do we get? And we found a formula for it. And the length of the curve, which is given by a function, by the graph of a function, was the integral from a to b of the square root of 1 plus f prime squared dx. X was the variable, and I had no issues. Now, the problem is different, slightly. Now, my curve is not given necessarily by a function like here. My curve is given parametrically because I'm allowing my curve to be like this. So the graph is not necessarily given by a function. And in this particular problem, in this situation, the question is how to find the length of the curve. Okay, so now the problem is I have a curve given parametrically. So let us assume this is my curve. Again, this curve cannot be given by a function. So this is my curve C, and it's given parametrically by 2 equations. X as a function of t, y a function of t. And I'm going to assume in this particular case that this curve doesn't go to infinite. So the domain is for the parameter is between alpha and beta. So it means in my mind, I have here a t, that's the t value. This is alpha, this is beta on the t value. For t equal to alpha, I'm assuming I am right here. For t equal beta, I'm assuming I am right here. So the first point corresponds to t equal alpha, and this point, and the reason we use alpha beta instead of AB is because we used AB for the length of the curve. So now we're using different letter of the Greek alphabet to determine the domain of alpha beta. And the question now is, what is the length of this curve? Means this curve right here, this curve, if you take it and stretch it, how much is gonna measure? That's really what the length of the curve is. So we have a formula. And how do we get those formulas? So first, there's condition. Suppose C is given by that, and the curve is traversed only once. Only once. It means when we sketch the curve, there is no room to go like this and back up. There is no room to go around the curve twice, which is, I will give you an example like that. So the curve is traversed one because I want actually to measure its length. So if I go around it 3 times, I will be measuring the length 3 times basically. So only traversed once, not twice. So how are we going to find the length of this curve? How do we answer those type of questions usually? You guys remember? How do we handle those type of problems? Whenever I have an issue, how do we do it? Anybody have any recollection of that? Any idea? Those formulas don't come out of nowhere, as you guys know. We work with them. How do you think I'm gonna, if you find the formula? Ideas?
I think we just have to represent the graph as a function of time. Am I wrong?
The graph is a function of time.
Yeah.
Yes.
But we have to graph it. We have to find t equals something so we can see it as a function.
We can't. There is no way out. It's not. If y cannot be written as a function of x. I can't do that. I have to work with it the way it is. I cannot go backward. I cannot go backward. Pure and simple. I'm going to use what we did the first part of the course. What did we do in the first part of the course? If we have an issue, what do we do with it? Integral. To find, we don't want area though, Sarah. What do we want? We want length. I don't want area. I want the length. I don't want area. So how am I going to compute the length? Just an idea. Let us remember, what do? We actually, the way we're going to, so that's the length. So how are we going to do it? We're going to split basically this into pieces. What we did day one, what we did at the beginning of the semester. And we're going to compute those lengths. Each one of them by itself, we're going to add them and see what we get. That's really the approach. We don't have any other approach. Now, how I will divide this curve into pieces. I will divide them like this. Since everything is in terms of t, y is not a function of t or anything, I will divide this interval the t interval into pieces. So I will call this T1, T2, etc. So there is etc. here, Ti and Ti plus 1. So I will divide the t interval into pieces. And then this is, I will call this point P1, this point P2, etc. This point Pi, and this point Pi plus 1. What is the point Pi? Pi is the point that corresponds to the time Ti. So Pi will be the point that has for coordinate x at Ti and y. Pi plus 1 is the point where the particle is at time t plus 1. So it's x at Ti plus 1, y at Ti plus 1. So we will do exactly what we did at the beginning. But in this scenario, because everything is a function of time, it's the time interval that have to be split into pieces. And now I will do exactly what we always do. I compute the length of every line segment. Means I want to compute the length of that. And then I'm going to add those lengths and come up with the nice formula. What is the length of every line segment? The length of any segment is the change in x square plus the change in y square. So here I will have x at Ti plus 1 minus x Ti square plus, so that's the change in x, square, y at Ti plus 1 minus the y at Ti. So there is no way out. I'm finding the length of this interval. Now the only game I will play is the following. To make this, I'm going to take this piece and I'm going to divide here by delta t square. So I want to divide, that's the only game I'm going to do. I will divide the inside by delta t square, but since I don't want to change anything, I have to multiply by delta t square and I can take it out. So I will take every interval, every segment, and I find its length following that. And now let us analyze, let's see if you guys can help me out. So this is going to be almost equal to what? This is delta t. I'm not changing it. What this term become close to? I'll write it by itself. I will totally isolate it on another piece of paper so you will see it and you tell me what it is. I'm going to focus on that term. That's x at Ti plus 1 minus x of Ti. And the delta t is Ti plus 1 minus Ti. The delta t is from here to here. Over delta t, the whole thing squared. Now when delta t becomes small, this expression becomes what? It's x of Ti plus 1 minus x of Ti over the delta t. When delta t becomes small, this is exactly the derivative of x with respect to t. That's what it is. Or dx dt square. So this piece becomes dx dt. So I'm switching everything in terms of time. I have to because my expression is a function of time. Now I can do the same for y. So this piece here is going to become almost the derivative of x with respect to t squared. And this will become the derivative of y with respect to t squared. And that's the delta t. So that's how the formula is going to really be brought. So now at the end, I'm going to add to the total length. Now the total length is going to be the sum of the length of my line segment. So it's going to be the sum of expression of the following form. This is my delta t, and those are going to become the derivative square plus the derivative square with some problem in the notation. This is going to give me a Riemann sum, and this will bring up the general formula. And the general formula will be t is my variable, that's my variable. The inside will be the derivative of x with respect to t squared plus the derivative of y with respect to t squared, and the interval is the interval of t, alpha to beta. And that's how the formula will be obtained. So this takes us back to the beginning. That's the only way we can find formulas for almost anything we work with. We split them into pieces and we work with them piece by piece. Okay, now this being said, let us do two problems along those lines. The first is a simple one, and they are both simples. And here is my problem. Suppose I take the following curve. And I'm going to take the simplest possible scenario. Cosine theta or cosine t. So let me start with a new paper. I'm going to call it cosine t, not that it matters, but I'm going to call it cosine t. So example number one. So suppose I have the following curve C, and x is cosine t, y or 4 cosine t, and y is 4 sine t. That's my curve. Now, if I graph the curve, it means I let the parameter t vary. What type of graph do we get? Do you guys remember what this should give us? So if I draw all those points that satisfy x equal 4 cosine t, y equal 4 sine t, what type of pictures I should get right here? Let's remember a circle, because if we isolate the x, like what we did yesterday, remember, sorry, when we isolate the x, we got x over 4 equal the sine, y over 4, I meant the cosine, y over 4 is the sine. And then we use the trig identity, cosine square plus sine square equal to 1. Cosine square is x squared over 16. Sine square is y squared over 16. It looks like an ellipse where the a and b are equal. We multiply by 16. This will give me x squared plus y squared equals 16, which is an honest to goodness circle centered at the origin where the radius is equal to 4. So physically, this is the graph should be on the circle right there. And I'm going to put restriction on t. So t is between 0 and 2 pi. Now, under this restriction, let us remember where we start. At t equal to 0, x is cosine 0. Cosine 0 is 1. So x is 4. And y is 0. So I'm starting right here. That's where we're starting. As t increases, the cosine, we know that as t increases, the cosine decreases. It means the x coordinate is going to move this way. And the sine increase, it means the y coordinate move up. So this is a circle going that way. And are we going around the circle once or twice? Okay, t is between 0 and 2 pi. Means at t equal to 0, we're here. At pi over 2, we're going to be here. Pi, we will be here. 3 pi over 2 will be here. 2 pi will be here. So we will go around the circle actually only once. So what's the length? Now we know what's the length of the circle, but we're going to use the formula just to make sure that that's exactly what it is. The length of the circle, that's a circle. It's 2 pi r. In my case, that's the circle of radius 4. So if I compute the length, we should have 8 pi. Now let's check out that that's what we get using the formula. Formula tells me the length is the following interval. Alpha is 0, beta is 2 pi. From 0 to 2 pi of the square root of the following quantity. X prime, derivative of x squared, plus the derivative of y squared. That's the formula for the length. So let us compute each one of them. What's the derivative of x? 4 sine theta minus 4 sine theta. So I will be patient and write it exactly. The derivative of y is 4 cosine theta t dt. So finally, I will get the integral from 0 to 2 pi of. This will give me 16 sine square of t plus 16 cosine square of t dt. So it doesn't turn out to be a hard one. So this will give me the integral from 0 to 2 pi of. Now, of course, we factor out the 16 because we see that something is showing up in here. And that will give me the sine square plus the cosine square. Now we use the fact that this is 1, and this will give me the integral from 0 to 2 of the square root of 16 dt. Square root of 16 is 4. I can pull it out, and I will end up with dt by itself. Now, what's the integral of dt? That's a t between 0 and 2 pi, which is 4 times 2 pi, which is actually 8 pi, which is what we hope to get, because what I am doing is finding the length of the circle. Okay. Now, let us say I take the following. I take the following problem. I will take, not a hard one, I will take x is, let us say, cosine 2t. And y equal the sine of 2t. And I will let my t go between 0 and 2 pi. Now let me put 4 because it's not really basic. Let me put 4. Okay. Now, this is a parametric equation. And I want to first graph it. Okay. Now, question number 1, the graph in this should look like what? And question number 2, what's the direction of motion and what's really going on as far as a particle moving along this? So question number 1 is, when we graph this, are we gonna get a circle? Yes or not? Back to you. Yes, because for the same reason, there is nothing. Cosine squared 2t, so I will get a circle. I know that. I will get a circle, and the radius of the circle is going to be 4. Very good. Question number 2, how many times are we going to go around the circle? That's important because I have 2t here. So how many times are we going to go around the circle? And we're going to go twice around the circle. That's important. Now, I can show it to you by plotting points. Let's see, by plotting points, x and y. At 0, the x is the 4, the y is the 0. At pi over 2, what is my x? Okay, it's cosine. So think of it as a time. Think of that as a time. At t equal to 0, my particle is right here. At t equal pi over 2, where is my particle? The x is cosine 2 times pi over 2. It means cosine pi. Cosine pi is -4. pi over 2 times 2 pi, that's a 0. So at t equal pi over 2, I am right here. So if I compare this one to the graph of x equal 4 cosine t, y equal 4 sine t, there is an obvious difference. If a particle is moving following this parametric curve, at t equal to 0, it's right here. At t equal pi over 2, it's right there. However, when I put 2t, it's going twice as fast. So we are really, really moving, but we're actually moving much faster than before. So now you can see the picture. At pi, I am here. So t equal to 0, I am here. T equal pi, I am here. So I went the first time around. Then to go back to 2 pi, I will go around this twice. So when I use the formula to compute the length of this curve, now the length of this curve is 8 pi. Nothing changed. That's really the length of the curve. But if I use the formula and I compute the length, what are we gonna get? When I compute the derivative here, I will have 4 sine 2t or minus sine 2t times the derivative of the inside. So I'm gonna have basically 8 cosine 2t squared. And again here, because I have this inside function, it's going to be 8 cosine t squared. So when I do the math verbatim like I did a minute before, I will get the 16 pi. I will not get the length of the curve. I'll get twice the length of the curve. The reason being, we go around it 2 times. So with this being noted, the formula for the length is used only when we know that the curve is traversed only once. Otherwise, we will not get the length of the curve. It's period. We don't get it. Suppose we go around the curve 5 times, it's hard for us to know, or sometimes we can go around the curve, part of it 2 times and part of it 1 time. So the length will be nonsense at this stage. So we use the formula if we go around the curve only once, not twice, nothing, just once. And that's will be the case. All right.
How do we figure out how many times it's going around?
We have to graph it.
Okay.
There's
So
no way out. Yes.
if we know how many times it goes around, why can't we divide that to find?
Because sometimes some curves will go around one piece more than once. And it will not do that for others.
Okay.
Okay, so it's really, that's why I cannot give rule. Otherwise we would. Otherwise we would. That's why we cannot really, we use this formula only when we go around it 1 time. Okay, and the only way you can do it, because graphing those really is not always, the one I'm giving you are easy, but they are not really easy to graph. That's why if you guys play with the program, I use Desmos, and just see how bizarre graphs could be. They could be really, really, really bizarre. Okay, any other questions? All right, so tomorrow is your quiz as usual, and we're gonna start the last ideas in this course, which is polar coordinate, which will carry us all the way through almost the final. It's important, but it's not a hard topic to talk about. All right, any questions, guys? Anything? So for tomorrow, your quiz will cover everything about ellipse. Show you, not ellipse, sorry. Everything about conic sections and everything about, if I give you quadratic equations, how you can complete squares. You should totally know how to do that to be able to get an ellipse or hyperbola or a circle in the standard form. So you'll be responsible for that. You will be responsible also for everything about parametric equation, and I will give you an integral based on the review I gave you. So far I gave you by parts, and I gave you partial fraction decomposition, and I urge you to do the problems. So tomorrow you will have also a problem along those lines. Any questions? Anything? All right. As usual, meet me in my Zoom office hours if you have any questions. Good luck, guys. Bye.